Hello everyone, welcome back to VCodes, a place where we discuss things related to VHDL, Verilog and anything general in FPGA. So in today's video I want to show you how you can use the built-in IP cores available with AMD Vivado. These IP cores are really great in the sense that without doing any coding, any VHDL or Verilog coding, you can set up complicated projects with these IP cores. So without any delay, let's practically see how this can be done. Alright, so let's start with creating a project. So this is the opening page of Vivado. We create a project. Next, project name, let's say test YouTube. This is the location, that's fine. Create project subdirectory, good. RTL project, let's leave it at that. And okay, we don't have any source files right now, otherwise we could add them here. So we can just go to next. Constraints we don't have, so let's go to next. So here, I mean, it depends on what board you have, what you want to select here, but since it's just for a demo, I'm gonna just choose this one. Just anything is fine for the purpose of demo. So next, alright, this is the summary, looks good, finish. Let's wait for it to create the project and initialize it. Okay, I think we have it ready. So you can see the design sources, which is empty because we didn't add any files yet, we haven't created any yet. So let's create an IP core first, and then we can write a test bench code for it to test whether the IP core is really working or not, right? So how do we create an IP core? So you can see here IP catalog. If you click on it, it has all the IP cores available in this Vivado edition, right? So we can use any one of this. So there is a lot of stuff here, like so many things. So for the sake of this video, I'm gonna just create an block RAM IP core. Okay, so what we can do is just we can search for BRAM, and there are, like, we don't want these controllers, we are gonna use this block memory generator. So when you just click on it, you can get some description what it is and few other info. So if you double click on it, it will open up a window where you can choose the settings for this particular block RAM. Yeah, so these are, so on the left side you can see the ports. So if you click on the plus sign, you can see for the BRAM port A, these are the signals. Yeah, and if you have a dual port RAM, so if you change this memory type to say simple dual port RAM, then even the port B becomes active, so you have more signals. So that is how it works. So depends on the settings you choose here, some of these signals will which is grayed out now but can get activated. Yeah, so we don't want a dual port RAM, we want a single port RAM. We want to keep as simple as it is possible for this particular demo. Yeah, show disabled ports, if you click on that, if you uncheck that box, it will show only the active port, which is port A. Doesn't look good, so let's click on that. Let's enable it. So interface type native is fine. Write enable, we don't need that. These things we can just leave as that is. Algorithm, let's leave it as minimum area or low power, doesn't matter for this demo. So that is the basic settings. And for port A options, 16 bit is the current width of the RAM. the default width. I'm going to make it 8. No reason, but I'll just make it as 8. And write depth. Next is the write depth, the number of elements of the RAM. So here it is written as 16, but I'm going to just make it into 256. Yeah. What I meant by 256 is this RAM has 256 locations, and each of that location is 8 bit in width. That's done. So if you look at the port A, you can see the address is 7 down to 0, which is 8 bit, because we have 2 raised to 56 locations. And D in and D out A are like the data which is going into the RAM, and D out A is the data which is going out of the RAM, which are also 8 bit in size, right? So operating mode, write first, read first, no change. So these things, when you just hover over here, you can see explanation for each of this mode. So depends on how the rest of the project is connected with this block RAM. You can choose one of this. Yeah. So I will choose no change again, just to make it simple. So enable port. So do you want an enable signal for the block RAM? So it's good to not enable the block RAM when it's not used for many clock cycles, right? That will be helpful in saving power. So I will use an enable pin because I don't want to keep it enabled when I don't really need it. And we can leave the other things as such. Yeah, looks good. If you look at this individual signals, address A is good. That is the address of the memory location which we want to write or read, and there is a clock A, which is the clock system clock signal passed to the block RAM. D in and D out A we have already explained. ENA is enable signal for the port A, and there is a WEA, which just simply means that write enable write enable signal for port A. Now also one thing, note that there is the component name here, so you can change that to something. Let's put it as BRAM test. Yeah. And there is other options. So in other options, mainly the thing I want to discuss here is, so if I just click on this one, what it does is it will initialize all the memory locations to 0 when on power up. Yeah, everything will be 0. So if without writing, if you read all the values after a power up, after powering up your FPGA, everything will be 0. But in some cases you already know what values there should be. So in that case you can load an initialization file. It has an extension of COE. So we can do that in this memory initialization part. So how do we do that? So first we enable this with the checkbox, and then you can do, either you can browse for the file which you already have, or you can just edit, then it will say, yeah, no CE file is specified, so create or choose. Yeah, I want to create, yes. So there is already a file here because I tried it out before, but if it is not there, we can also write something up here, like say BRAM demo. Yeah, that's the new COE file which we are going to create right now. So save, and it says, okay, you need to enter two values, 2 data points here. So first is the radix. So either you can give it as a binary numbers, or you can give it as hexagonal numbers or decimal numbers, and so on. So I'm gonna keep it simple and give as decimal numbers. So what I will do is the radix will be 10 in that case, right? 0 to 9. And the memory initialization vector. So it will, so first if I mention 1 here, it means that the 0th location will have the value of 1 initialized on power up. So what I'm going to do is, just for testing purposes, 1, comma 2 comma 3 comma 4 comma 5. So memory location 0 to 4, I want to initialize them with decimal numbers 1 to 5. Yeah, and I save, and then I can click on close. So that is done. You can see that the BRAM underscore demo CO is been created, and it's set here. Okay, so I think we are done with the settings. We can check the summary to make sure that everything is good. Single port memory. So these are the inbuilt sources which will be used by this IP core. So we have chosen as 256 depth for our BRAM. So it uses an 18K BRAM. We don't need a 36K BRAM for that. And total port A read latency. So this means that when you give an address for reading, it takes 2 clock cycles for the output to be available at DOUT A port. Yeah, so that is quite unfortunate, but that is what you get. And the address width is 8, which means 2 raised to 8, 256 locations can be accessed with this address port. So since we are satisfied with that, we can click OK. Okay, customizing the IP. And these are the files which are going to be generated. We can leave everything as such, and we click on generate, and now it's generating all the necessary files for using this IP in our project. Let's wait for that to be done. So once this thing is created, it will be automatically added to the project, and it should appear in the design sources over here. Yeah, IP core has been created and it updated. You can see the BRAM underscore test is already here. It has the file extension of XCI, and if you double click on this, the IP settings window will open again, and you can again change things here and then regenerate the IP core as per the new settings. So that is one really nice thing to remember. So what you can do is you can even click on this little arrow. Okay to show IP hierarchy. It will take its time, but let's click on OK. I want to show you something. What it's gonna do is it's gonna show you the VHDL file for it, not the whole IP, but the external wrapper and the settings and all that. So that will be helpful in getting to know what the VHDL port looks like for this BRAM. So when I double click that VHD file, this thing opens up, and the main thing which I want to focus on is this part. So this thing is needed so that we can instantiate this RAM, this block RAM in our designs, right? Even if we are going to write a test bench, which we will do now in a bit, we need to know this. What are the input and output ports? What are their names? What are their sizes? Yeah. So this is how you get that. Clicking on this XCI file and then double click on the VHDL file, which will be generated. Yes. So now I want to write a test bench code. So test bench code has been already created. It is available in my VHDL blog, and it is this one. Yeah. So in my blog I have done the same example, and there are some screenshots available. So if you don't want to watch the video or want to refer to it in detail by reading, you can go and check it out. So the code is available here. Yeah, I named the test bench entity as tb_bram. So we can just copy this whole thing and then go here. Let's create a simulation source. So add sources, right clicking on simulation sources, add sources, add or create simulation sources. Good. Next, add files, or no, we are going to create a file name tb underscore bram. This is the name of the entity of the copied code, so we will keep the same. Okay, and I think we can click on finish. Okay, click on OK. This has not been changed. Are you sure you want to use these values? That's fine, because we are going to overwrite. We don't care what kind of file will be generated by Vivado, because we have the code already copied from my blog. So it's still running. Again, the process is being run here. You can see it on the right top. Once that is run, VHDL file will be available under simulation sources. We can double click on it and then paste the code which we have copied from our blog. Okay, it should be ready now. Yeah, here. So this is something which is generated by Vivado. So I'm going to just Control A to select all and Control V to paste whatever I copied. Yeah. So we have the code here. So you can see that this component BRAM underscore test, which basically I copied from this file over here. Yeah, this is how I got this part, and everything else remains the same. These are the internal signal declarations. This is where I instantiate using named association. Named association means name for the local signals and the signals within the design are both specified, so it can be in any order. Yeah, and this is I generate a clock so that I can apply to the BRAM, and this is the stimulus. So I am trying to read the addresses 0, 1, 2, 3, 4, 5, 6. So 0 to 4 should contain 1 to 5, values 1 to 5, and 5 and 6 should have a 0 in them, right? Because that is how we initialize the BRAM. So now we click on Control S to save the file. So now we click on simulation, run simulation, choose behavioral simulation. Once you do synthesis, there is option to do post synthesis and post root simulation, but we are going to stick with simple functional simulation in this video. Okay, so this is the simulation window. You can see that all the signals of the test bench is shown here, and so you click on the waveform and then you can click Control and then use the mouse scroll to zoom in or zoom out. So yeah, this looks good enough. So you can scroll to the beginning and you can see that this is the enable signal, and 0 is the first address which is sampled on the positive clock edge, and for 0 the result comes in the next clock cycle here, that is 1, and for this one the result comes again after 1 clock cycle delay, which is here, and similarly 2, 3, 4, 5. So this D out A corresponds to this address, this address. This D out A of 5 corresponds to this address of 04. You might remember that in the IP settings we saw that there is a read latency of 2 clock cycles. Yeah, so that is why this delay is there. And for address 5 you get a value of 0, because we didn't initialize it with any particular value. We set all the remaining locations as 0, and for address 6 is also 0. Yeah, so it seems to work, it seems to initialize properly. So that is how you work with a Xilinx, not Xilinx, AMD's IP catalog, AMD Vivado's IP catalog, to generate an IP core and then instantiate in your design for testing or using it for a bigger project, and so on. So that's all in this video. I hope it was useful to some of you, and if you have any doubts about this, you can write a comment about it, and I will try to reply them. And if you need any personalized guidance for any of this thing, I am available for tutoring as well. So just get in touch. Yeah, okay, bye bye.